Well, we can apply the same principles to vertical circles. In other words, first of all, we know that if something's moving in a circle, there must be a physical force making it go in a circle. And that physical force, or combination of forces, must act towards the centre of the circle. So just like when we looked at the horizontal circle example, the same kind of rules apply, do the same steps. Well, let's look at a typical example where you have a kind of roller coaster situation. So you might have a sort of loop-the-loop job where you've got a guy in a roller coaster car, first of all at the bottom of the loop. So let's have someone just sitting in the cart there, and then later at the top of the loop. And questions love to kind of ask about this, and you know, in some different disguise, what's going on at the top and the bottom of a circle. It could be something in a washing machine, like a sock. It could be a roller coaster type ride, or so many things. So, and of course, this time the situation is a bit different whether you look at the top or the bottom. Well, let's follow our rules. So, well, step one, remember, is to label all the forces. So, well, we need to do that twice now. We need to do it for the top situation and the bottom situation. Well, we know that in both cases, if we're looking at the person and the force on the person, well, they're going to be experiencing their own weight downwards, and that's going to have the same value whether they're at the top of the circle or whether they're at the bottom of the circle. So in both cases we can label mg on our person who's in this loop-the-loop. So at the bottom of the circle their weight acts down, at the top of the circle their weight acts down. Now we're still on step one. We've got to label all the forces acting on the person. Well, if you imagine yourself being the person, say for example at the bottom of the circle, well, your weight's pulling you down, but there's also the seat you're sitting in is pushing you back up. So there's a reaction force pushing you up towards the sky, something like in this direction. And I'm going to make my arrow just a bit longer than the weight because I know that there are no other forces acting on me at that moment when I'm at that position in the circle. Assuming I'm going at constant speed around the circle, then there's no left or right forces accelerating me. So that's it, that's all the forces acting on me. My seat pushing me up, my weight pulling me down. But I know that R must be bigger than mg. Well, how do I know that? Because I know that those forces must combine to act towards the centre of the circle for the very fact that I'm going in a circle and the centre of the circle is above my head. And there must be a combination, in this case, of physical forces providing the centripetal force to make me go in that circle. So in the case when I'm at the bottom of the loop, those must be the forces acting on me. At the top of the loop, the situation is somewhat different because my weight's putting me down, but my seat is also pushing me downwards. So I really need to label the reaction force from my seat is also going to be in the same direction as my weight this time, and I'm going to label it R. Now I have no idea how big that arrow is going to be, because basically R and mg are going to combine this time. They're both towards the centre of the circle. They're both pointing above my head, which is now the centre of the circle, and so they must combine to make the centripetal force. So that's the situation. So, well, now we can move on to step 2, which says decide what is providing the centripetal force. Well, we need to do that this time at the top and then at the bottom. So let's start at the top. Well, at the top, it's pretty clear that it's going to be R plus mg, R plus the weight, which is providing mv squared over r. Whereas at the bottom, it's also pretty clear that it must be R minus mg, which is the resultant force towards the centre of the circle. And so I can write down an equation R plus my weight is providing the centripetal force for the top position, and R minus my weight is the centripetal force for the bottom position. So hopefully that makes sense, and that leads to something interesting. You know, the situation that the person experiences is going to be slightly different at the top and the bottom, or very different, because remember, we're assuming that the car is going round at a constant speed around the loop. Now, in reality, in a real roller coaster, that's a bit unrealistic, and also the real roller coaster loops aren't perfectly circular, but you do get fairground rides which are perfectly circular, and you know, you can imagine a kind of Ferris wheel type situation, whirling you around and around. So, well, what is of interest here is the force that the person, if you're sitting in that chair, what you're really interested in, what your brain is recognising, is the reaction force. We're always experiencing our weight downwards, but it's the push of the chair which is going to make us feel strange or different, and that's what roller coaster rides are designed to make us feel. So let's rearrange both equations for the reaction. Well, at the top, the reaction force, therefore, will be mv squared over r minus my weight, whereas at the bottom, it'll be mv squared over r plus my weight. So I'm going to feel heavier at the bottom. Because I'm moving in a circle, there's the centripetal force plus my weight is going to be pushing up through my body. So I'm going to feel heavier than normal. Whereas at the top, I'm going to feel lighter than normal, because the push of my seat pushing me down is going to be the centripetal force minus my weight. And we can kind of take this a step further, because we can see that, well, if I go slow enough, then the reaction force will actually become 0. So, well, r is 0 when mv squared over r equals my weight. In other words, when my weight is just enough to provide the centripetal force on its own, I'm going to experience no push. I'm going to kind of not be pushing onto my seat at all. So I'm going to feel kind of weightless for a moment there. And roller coasters are designed to make that kind of happen. And if you've been on any kind of roller coaster, you'll know that sort of feeling. At the bottom, you experience a bigger force than usual. And that's also part of the design. You feel that sort of high G-force effect as you go around the bottom of the bend. So questions like to play around with those ideas, which we'll look at later. And but hopefully that explains one example of what's going on in a vertical circle.